Good day, everyone. Today I'm going to tell you about modeled sound exposure levels for a marine seismic survey that was done in South Africa. So seismic surveys are done to locate reserves of oil and gas within the seabed floor. And what happens is a loud noise travels from the air guns through the different mediums and densities of the sediment layers back up to the hydrophones located along the streamer. These hydrophones then convert this data collected into like a 3D picture where you can locate the oil and gas reserves. So seismic surveys produce really loud noises. So this is what one sounds like. You can hear the engine noise, dolphin whistles, and then the loud bang. So this loud bang has been shown to affect marine fauna in various ways. And it can affect things from zooplankton all the way up until your large baleen whales. It can kill the zooplankton, it can kill fish, it can mask communications between animals, and it can increase stress levels. So a seismic survey, its frequency overlaps quite significantly with your large baleen whales, so they are affected quite badly in terms of their communication. So Southall et al. Determined the temporary threshold shifts and permanent threshold shifts for hearing within these groups over here. The large baleen whales, your low frequency animals, your high frequency dolphins, your sperm whales and your dolphins, your very high frequency animals like your porpoises, and then your sirenians and seals, your true seals and your non-eared seals. Okay, so temporary threshold shifts occurs when the animal becomes temporarily deafened, kind of like when there's a loud bang that goes off and then you hear ringing in your ears. Permanent threshold shift is actually when the ear is damaged and hearing deteriorates. They can become deaf. Okay, so the aim of this was to determine the sound exposure level of a 3D seismic survey and then find out what the potential sound exposure level received by the marine fauna was during the survey, and also highlight the need for specific mitigation measures specific to South Africa. So South Africa, before a seismic survey is conducted, an impact assessment and management plan needs to be produced, and this is then vetted by the Petroleum Agency of South Africa. However, it's generally based on the JNCC regulations, which are more suited to the North Sea. Okay, so the study area was in Algoa Bay, which is in the Eastern Cape of South Africa, and you can see here this red area is where the survey occurred, about 25 kilometers away from the MPA, the bird island. This is where the African penguin lives, and they are critically endangered as their population has decreased by 90% in the last 10 years. And a recent study has shown that they're affected up to 100 kilometers away from seismic surveys. So the fact that it was only 25 kilometers away from the MPA is a bit worrying. Also, this area contains, is home to the Cape fur seal. Sperm whales occur there, Brewer's whales. Brewer's whales are quite special. They are different to other baleen whales and they don't migrate. These are resident in this area, and Penry et al. Have just published data that show that they are genetically different to the Brewer's whales in the Western Cape, which means their numbers are quite low. Also in this area is the endangered Indian humpback dolphin, although it shouldn't come out as far as the seismic survey as it is a very coastal species. So the methods, originally when I started this project, I thought, okay, yes, I'm sure it'll be difficult. Physics is not my strong point, but these steps, hopefully I'll be able to follow. Little did I realize that these steps include many other steps within each step and a whole lot of figures that I struggle to understand. Anyway, I'm getting there slowly, but because of that, I don't really have the results I should have at the moment. But yeah, hopefully in the next few months that will be finished. So what you need to do is model the acoustic output of the seismic source and then convert this into third octave bands. Then model the transmission loss and calculate the received level of sound and convert it to sound exposure level. And then determine the cumulative sound exposure for the marine fauna seen during the survey. Because seismic surveys release sound every 10 seconds into the ocean, and this can be done over a period of weeks to months, depends on how long the survey is and how big an area they need to cover. And then I want to determine the impact ranges for the temporary threshold shifts and permanent threshold shifts in the survey for the different groups of marine fauna seen, and then filter the weights according to Southall et al.'s M weighting criteria. Okay, so the marine fauna seen during the survey, I split up into the groups as determined by Southall et al. So you have the low frequency cetaceans, which includes your baleen whales, your high frequency cetaceans, which in this case the marine mammal observers, which are placed on the seismic survey to mitigate against the effects of seismic surveys during real time during the survey itself. They saw false killer whales, common dolphins, and then a number of unidentified dolphins and sperm whales. They also saw a lot of seals, Cape fur seals, and African penguins. So the distances ranged between 600 and 6,000 for the baleen whales, and African penguins and Cape fur seals were very close, and so were some of the dolphins, 300 meters away. And this was all during full power of the survey. Okay, so to calculate the acoustic outputs from the source, I used Agora, and it solves a bunch of differential equations iteratively, and this is done in MATLAB. So a number of inputs are required. For starters, the geometry of the gun array, and in this case there were 33 air guns, all with different volumes, and you can see in this diagram how they were all laid out. Then you also need the sound of speed in the water, the receiver depth, frequency, and azimuth angle. And all this data was provided to me by the Petroleum Agency of South Africa for this particular survey. So results, this is a polar plot showing energy source spectral density as a function of frequency. And this one also is a energy source spectral density as a function of frequency at an elevation of 20 degrees at an azimuth angle of 0 for both of them. Okay, so this diagram shows the direction pattern of the seismic bang split up into the 3rd octave bands. It just shows you that the different frequencies all behave differently depending on the frequency. Here you can see the frequency split up into the 3rd octave bands and the decibels that each one produces. So each frequency produces a different decibel when the gun goes off. Okay, so now I summed up the 3rd octave bands logarithmically, and then got this spider plot, and this is for each azimuth angle all the way from 0 to 360 degrees, and it shows you the decibels produced during each azimuth angle, and that's summed up over all the 3rd octave bands at a horizontal plane. So it's horizontal. Imagine it spreading out over the water sideways like this. And this diagram here is the vertical production of the sound. So this value here is at 90 degrees straight down onto the ocean floor. Transmission loss, I did it in ActUp. It's a user interface toolbox run in MATLAB as well, and which is a parabolic equation for elastic seabeds, and it is range dependent as well. So the inputs are similar to what I required in Agora. You need bathymetry, but for bathymetry I extracted the depth every 500 meters along each azimuth angle. And then you need geoacoustic data and the sound of speed in the ocean. So I picked a radius of 50 kilometers so as to include Bird Island as well and the MPA. Results of transmission loss. Okay, so for the geoacoustic properties, it was pretty scarce, and I did determine that the sediment was predominantly medium grain sand, and then I extracted the rest of the data from Jensen et al. It's compressional wave velocity, density, and wave attenuation. For thickness and depth, I didn't have that information, so I classed it as a bottom half space, which is a mathematical model used to approximate the Earth. Here is the bathymetry for 0 degrees azimuth. So you can see it starts at about 93 meters deep and then goes up. So it goes shallower towards land. This is the transmission loss, depth and range. So as depth and range increase, so too does the transmission loss. And you can see it for the different frequencies, 8 Hertz, 125 Hertz, 250, and 500 Hertz. These are just a selection of the center frequencies used in this study. So what next? I need to determine the sound exposure level. So I need to combine the source level and the transmission loss. And then with that information, I will create a sound map. And then I need to filter the results using the M weighting as proposed by Southall et al. For each of the hearing groups, and then determine at what ranges would temporary and permanent threshold shifts for each animal occur during this seismic survey. And then also calculate the cumulative sound exposure level for each of the marine mammal groups seen during the survey. So I just want to thank the MRI Well Unit, the Eugene Murray Chair of Wildlife Management, Petroleum Agency of South Africa, Alec Duncan and Jan Doe for their help with UCTUB. Thank you.